Be quiet. That's so weird. It's like a
That is a weird M, isn't it?
Unless you like build houses.
Okay, I need you working on this, please.
Wow. Okay, I got it.
Okay, what did we get? 40. Okay, now how'd you get it?
My neighbor.
That's okay, that's fine. What's the, more importantly, well, we'll get to the algebra, but let's start with the geometry, right? We're going to, solving for x implies that we're going to do some algebra here, right? We're going to come up with some equation that we can solve for x. But before we get there, we need to know what's the geometry relationship that's going to give us that equation. What's going on? What kind of angle pair is that? What relationship do they share up here? Are they vertical angles? Are they alternate exterior angles? Are they? Okay, yeah, but I want to know what kind of a
Something interior.
something interior. Yeah,
Interior. Is it consecutive?
consecutive interior. Okay, consecutive interior. Why are those consecutive interiors? Okay, they're on the same side of the red transversal, and they're inside the two lines, so they're on the interior, right? So consecutive interior. Okay, now do you remember see if you can get your little list out real quick. Get out those lists of theorems and postulates and definitions and all that stuff. And I want you to find the reason why that we might exploit here.
What is that?
Which one is it?
You got it yesterday. Barbie.
It's right there. Is that it?
Nope.
Sure. I think you're missing maybe one on that. I think I've got one for you here. Hang on.
Okay.
What kind of boots are those?
Oh, I lied. No, I don't. I'll print some more later. It's in Moodle. You know, it's that thing you pull up in Moodle. Okay, so there really are two possible. Hey, I need it quiet, please. I need you with me here. This is serious time. We'll go to the lab maybe if we have time, but right now it's not looking good. There are two possible answers that I would take for this. I mean, what are the two theorems that might apply here, that might relate? What's one of them? Okay, consecutive interior angle. Consecutive interior angle theorem, technically. We don't care if it's a theorem or a postulate. So consecutive interior angle relationship, that's the one that says if two parallel lines are cut by a transversal, then consecutive interior angles have to be supplementary. Good, okay. That would work. That's the one that we use if we're doing a proof, let's say, or we're trying to find the value of an angle. That's the one that we would use if we already knew the lines were parallel. That would be an okay one to use here, though, in a way, because we're trying to make those lines parallel, right? We want to know what's the value if those lines are parallel. Now, how does the converse of that one go? If the consecutive interior angle theorem says if two parallel lines are cut by a transversal, then consecutive interior angles are supplementary. How would I do the converse of that one? How do I flip that around? If what? Okay, if the consecutive interior angles are supplementary, right, then what must be true? The lines are parallel, right? Either one of those really would be okay here. That's fine. Now we call that the consecutive interior angle converse, because that's the backwards version, right? Either one of those would work. Either way, what's the algebra relationship we get between these two angles? What do they have to, in order for these lines to be parallel, what has to be true of those two angles? Yeah, they're supplementary, so they add to 180. Good. So 2x plus 3x minus 20 equals 180. And how would we go about doing that algebra? Okay, like terms. So 2x and 3x is 5x. What about the 20? Push it to the right. And then there's how you got your 40, right? Dividing by 5, both sides by 5. And so we get x equals 40. Very good. Okay. All right, so there's just, that's kind of the stuff we were looking at recently, last couple days. Let's take a peek here at 3.5.
I like how many buttons you have to press.
I know.
You tap it like you're
Yeah.
I know, every time you're like, it's like, okay.
Okay, using parallel lines. So what about this one here?
Oh, why is that line right there?
Right where?
Is that the doctor needs?
Oh, right here?
No.
Right there?
Yeah.
Oh, I don't know. I didn't pick this back. I promise you. It's very crafty, isn't it? So in this case here, we're going to prove two lines are parallel. Lines M, N, and K represent three of the oars of a team of rowers. So I guess what we're sort of assuming here then is maybe this is the boat. You got to use your imagination.
Oh, I gotcha.
I see it.
But you see the boat? There's our boat, and there are the oars sticking out the side. Okay, and they're going to just kind of sweep backwards and push the boat forward. You
Are
see
they
the
on
picture?
Both sides or just one side?
Well, that's just one side right there. Maybe there's some on the other side too.
No, those are really big oars.
Those are pretty big oars. In fact, they're infinite oars, aren't they? But if that's the situation that we're modeling with this geometry drawing, we want to prove something here. We're told that lines M and N are parallel, right? And we're told that lines N and K are parallel as a pair, and we want to prove that lines M and K then are also parallel. Okay. Now it makes sense probably. You almost might want to just say, well, it's just so obvious. Why would you prove it? It's a good question. But sometimes in math, things that initially seem really obvious, that are just, there's just no point in even thinking about them, don't turn out the way you think. Every once in a while, you're going to get surprised. And so we're going to go through and prove this. And you're right. I mean, this one is pretty obvious. And M and K are parallel. And when we're done with this, the result is we're going to have another reason that gets added to our list. It's actually already on there. That we can use in other proofs. But we got to prove it at least once. We got to show that all the steps between what's given and what we're trying to prove make sense and are reasonable statements. They're statements that we all agree on. Okay, so let's just talk through it first, and then we'll throw it up on the board as a two-column proof and see what it looks like that way. What do you think? What are some things maybe we could do here? What could we do with this? If we're given that M and N are parallel, does that help us relate any angles, for example? What's it tell us? Which angles? Now, if M and N are parallel, 1 and 2, okay. And why? Okay, now what's our reason? If you look at your sheet there, if I've got two parallel lines that are cut by a transversal, why can we say that those two angles are congruent? We're correct in saying that they are. But what's the reason? What do you think? What's our reason for that? Corresponding angles. Technically corresponding angles postulate, but they're corresponding angles, right? That's why, okay? So 1 and 2 are congruent. Very good. Angles 1 and 2. Now, what about if we focus on angles N and K? We're told those are also parallel. What do you think, Justin? 2 and 3 are congruent for the same reason, right? Okay, so 2 and 3 are also congruent. Now, that helps us. Now, look at the very top of your list up there. Before we can get to chapter 1 and the general ones, do you see a reason there why we could say that now if 1 and 2 are congruent, and 2 and 3 are congruent, is there a way that we could relate 1 and 3 as also being congruent? What do you think? Good. Transitive property of congruence. We can transfer that congruence, right? So now we know that if 1 and 3 are congruent, now what? Now ultimately we're trying to show here, remember, that M and K are parallel. So we just showed that yes, angles 1 and 3 are congruent. So now, here's the last reason we need. One more step. How can we show that M and K are parallel lines? I should be looking at your list. It's on page 2. What is that? Gotta find that one. Okay, there's the list, right? I want you to notice something here. I'm going to get rid of my little boat. I want you to notice something here. When you look at the chapter 3 stuff on this list that I've just pulled up, it goes in order. So here's really the 3-3 stuff. The first stuff we hit in chapter 3 that we need to add to our list of reasons is in 3-3. Corresponding angles postulate, alternate interior angles theorem, alternate exterior angles theorem, all of those things that we see in 3.3. Notice I put this in bold because it's so important. Notice that they all start with the same statement. If two parallel lines are cut by a transversal, then corresponding angles are congruent, or alternate interior angles are congruent, or consecutive interior angles are supplementary, etc., right? But if we scoot down a little bit to the 3.4 stuff, look what happens. Look at the converses, right? The converses, those are the ones that do the opposite. Those are the ones that we've got to draw on if we're trying to prove that lines are parallel. Because look what the last statement is. Then the lines are parallel. Well, that's what we're trying to show here, isn't it? That lines M and N, I think, those two, M and N are parallel, right? M and K. Trying to show that M and K are parallel, so we got to use one of these. Well, which one is it? If we go back to our picture, here's the angles we're looking at, 1 and 3. I see a hand back there. Yes, sir. Not alternate exterior, close. Now ignore this line in the middle. All we need are those, the top one and the bottom one. What kinds of angles are those? Ah, okay. So then which one is it? Aha. Okay, it's the corresponding angles converse. The converses are the ones that are backwards. Okay? Corresponding angles converse. Make sense? Okay? Good. So now let's look at what that, if we were to put this in the format of a 2-column proof, then what do we get? So statements. Well, we were told that M is parallel to N. That's given, right? That's something that's given to us. Because of that, we said then that angles 1 and 2 were congruent. You all told me the reason for that was corresponding angles. Yeah, I don't care about postulate. We looked at lines N and K. Those were given to us as being parallel. And so for the same reason that we had up here, 2 and 3 are congruent angles also, right, by corresponding angles. Then we said that, well, if 1 is congruent to 2 and 2 is congruent to 3, then 1 is congruent to 3 by transitive property of congruence, right? And then finally, we were able to say that, okay, well then if angles 1 and 3 are congruent, then M and K must be parallel by the corresponding angles converse. Yes. Okay. So there it is. Okay, very good. Okay, and so what we get out of this then is a new property called the transitive property for parallel lines. And all that says is if two lines are parallel to the same line, then they're parallel to each other. And now we've got that other reason we can use without having to go through that whole proof every time. Similar to that, we also get a transitive property for perpendicular lines, which just says that if we're in a plane, in a single plane, if two lines are perpendicular to the same line, then they must be parallel. Like, for example, here, line M is perpendicular to line P, and line N is perpendicular to that same line P. And so as long as we're drawing these on a single board or in a single plane, then M and N have to be parallel. Okay? All right, I'm going to skip that. Let's look at the CD rack one. This is good. So we're building the CD rack. You cut the sides, bottom, and top of the front so that the corner, the boards all come together at 45-degree angles like this. Let me draw in, it's kind of hard to see though. Let me do this.
Oh, the straight line.
How about that?
Oh, snap.
Ah, bro.
You got me.
Gotcha.
Always.
Okay, so there's the front of this thing. So we got this top piece right here. We got this side piece over here, side piece over there. I don't think I drew that in the right spot though, did I? Oh, I did. You get the idea though, right? Just go down a little bit. There. Okay, you get the idea. Right? Oops.
I like when you stand in front of things and the words come up on your bald head, so it's like you have tattoo on it.
You like that?
Ah, you're so funny.
It does, there's
How do I
that.
get rid of that?
Undo. Undo.
Oh, there we go. Okay. So let me go back. Okay, so right there. So now we got the, so you see the pieces, top piece, bottom piece, left piece, right piece. And what we want to prove here, what we're told is that we cut these things at 45s, right? So that angle right up there, that angle 1 is 45 degrees. Angle 2, 45 degrees. Angle 3, 45 degrees. And angle 4 is 45 degrees, right? And what else were we told? That's it. Okay, we want to prove here, our goal is to prove that segment BA, we can call it line BA if we want to, we can extend it forever, because if the segments are parallel, so are the lines. So segment BA is parallel to segment CD, or line BA is parallel to line CD. Either way, doesn't matter. So how might we do that? Let's talk through this one first, and then we'll see what it looks like as proof. What do you think? What's going to be, maybe, I'll throw any suggestion out. Is there ultimately some strategy that we're trying to get at here? What do you think? Is the fact that those are 45-degree angles significant at all?
Oh, 10.
Why is it, if they were 44, maybe it wouldn't have worked? How come it works because they're 45s? Ah, okay. Because if I add those up, 45 degrees and 45 degrees makes 90 degrees. Aha. Okay, so then we're able to do something like this. We know that this is a right angle up there, and that's a right angle down there, right? And now what? If those are right angles, what does that tell you about line BC, for example, and line AB? Ah, they're perpendicular, aren't they? Because that's the definition of perpendicular. If they meet at a right angle, then they're perpendicular. Same thing down there, right? So these must be perpendicular. Now what? We just talked about a new reason. If two lines in the same plane, they're both on the front surface of this thing, right? If two lines in the same plane are perpendicular to the same line, then what? They're parallel, right? Does that make sense? Now we got to just put the steps in there that match that. Okay, so how do we do this first part? If we know that these are given to us as 45s, there actually is a reason. Look at your sheet. What's the reason that says if I have two 45-degree angles together, if they're adjacent to each other, and I add them up, I get 90? What's the reason that says we can do that? goes clear back. I think it's a chapter 1 thing. I'm sure it is. First page.
Okay, segment addition postulate.
Well, we want to prove that that's okay to do, that if we add those two 45-degree angles up, we get a 90-degree angle. What's the reason for that? I hear it. Angle addition postulate. Look at that one. Okay, so that's the one that says if, well, you can read it to me. What's it say? What's that one say? So, right, we're looking up here at the very top, angle addition postulate. P is in the interior of angle RST, then the measure of RST plus the measure of PST, measure the whole thing. You don't have to think about it in that complicated a way. That's technically what it says. Maybe we could translate that into a way to think about it that's a little simpler. All that's really saying, isn't it, that if I have two angles next to each other, I can add them to make one big angle, right? Their measures add to the measure of the big angle, okay? Angle addition postulate. And I don't care about the postulate, it's angle addition. And then if it's 90 degrees, you already told me that 90 degrees makes a right angle. That's the definition of a right angle. And then if it's a right angle, these are perpendicular, right? Definition of perpendicular. And then from there on out, it was pretty easy. So let's see that thing as a proof now. And by the way, I think this is kind of a harder proof. This is a lot more steps in this than the kind that you guys are going to end up doing. Let me just put all the answers up here, and then we'll just look at them all at once. Oops, one too far. Okay, so here's what we said, right? Measure of angle 1 is 45, measure of angle 2 is 45. That was given to us. The measure of angle ABC, that was that top corner, right? Equal the measure of angle 1 plus the measure of angle 2. That's angle addition postulate. And its value was 90 degrees. I would argue that you almost don't even need to, well, I mean, that statement is pretty obvious. I don't care what you put for that, literally. I don't care. Technically, it's substitution, but you could just say addition, arithmetic, algebra. I don't care. This is a step that's not even really a geometry step. It's just 45 plus 45 is 90. I mean, we know that. Yeah, I don't think you need to justify that. Angle ABC is a right angle. Technically, definition of a right angle. But really, you might even be able, and I think this would be reasonable on one like this, to even just skip from there right down to there. That would probably be okay. I don't think it's a terrible crime to do that. Proof is still right in my opinion. Then we know here that line BA is perpendicular to line BC by the definition of perpendicular lines, because that's a 90-degree right angle, right? So look what we did then. We showed that the black part, I've color-coded this, the black part of that proof just gets us down to where we're showing that. Let me go back just a second here. We just showed this, didn't we? We just showed that this line and this line are perpendicular, right? That's what we did in the top part. Now if we scoot on down, okay, the blue stuff is just taking care of the bottom, right? Same, it's exactly, well, it's almost identical. It's analogous to that top one. I might even say it's parallel to the top one, but that'd be confusing. It's a parallel structure. They both do the same things. Measure of angle 3, measure of angle 4, 45, that's given to us. The bottom corner is the sum of measure of angles 3 and 4. Same thing we had up here, addition postulate, right? Angle addition postulate should be. Oh, I messed that up. Should be angle addition postulate. Sorry. I'll fix this when I put it online. Measure of angle BCD is 90. Yeah, that's just whatever you want to call it, addition. It's a right angle, definition of a right angle. So the bottom side and the left side are perpendicular by definition of perpendicular lines. Okay. You could just put perpendiculars as far as I'm concerned. And then finally, down at the very bottom, we get to the answer. Now, because we know that line BA is perpendicular to line BC, and line BC is perpendicular to line CD, okay? Then we know, I messed that up too, looks like, darn it. We know that line BA is parallel to line CD, okay, by the transitive property of, what do you know, perpendicular lines. Not parallel lines, I'll fix all that stuff before I publish the PowerPoint. Does that make sense?
Yes, sir.
That's a pretty big proof. But what I want you to see here, I'm not going to give you one that big, but I want you to see that even a big ugly proof like that, there's some structure to it. That if you think about it, you can see what the structure is. It's not as confusing and scary as it might have initially looked if you, once we've kind of gone through it. I mean, it makes sense. Yours will be shorter, but same idea. Okay? I just want to show you something, and I just want to, we're going to do our proofs this way, 2-column way, because that's kind of just how you do it at first. But there are other ways to do proofs. I think this, personally, is a much better proof than the 2-column proof. Now, this is what you might call a flow proof. Look what this is doing. It's saying that if we look at that upper right-hand corner, there's all the stuff that we did in black is sort of in this first little flow, right? This first little, we starting up here and the arrows are pushing us down this way. You know, we got some given information. Angle addition postulate tells us that these two add up to 90. And ultimately, we know that the top and the side are perpendicular, right? Over here, we got the bottom stuff going on. The bottom two angles of the boards are 45. We can add them up and get 90. So the bottom corner between the left side and the bottom is perpendicular, right? Those lines are perpendicular. Then it all comes together to show us that line BA and line CD are parallel, not perpendicular. Okay? By our same reason. Right? Makes sense? Transitive property of perpendicular lines. Okay? Get the idea? Isn't that kind of, I like that way better. To me, you can kind of visually follow that
Easier.
easier. I think it is. So you don't always have to do proofs in a 2-column way, even though we will this year. Later on in life, you won't have to. All right. How much time we got?
We have
about
like
12.
10 minutes.